So yeah, I'm trying to show you how we can use mechanical instabilities to create some form of complexity in the systems. And the complexity here would mean shape changing or patterning, or studying memory effects. And I will define what these memory effects are. And we'll go through these three systems that are depicted here. And we'll start with this one, the wavy black thing. This is called an electroactive polymer. This is something I studied during my PhD. It was at PMMH in Paris, under the supervision of José Vico and Benoît Roman. And an electroactive polymer the principle is extremely simple. You have a thin layer of an insulating polymer. In that case, that's VPS, so that's the simplest thing we could find. It's rather small. Here it's about 100 micron thick. And on each side, we deposit a compliant electrode. So here, that was carbon black powder. So that's something that does not change the mechanical properties of the system. So what you're manufacturing here actually is a soft capacitor, right? Insulating material with two electrodes. And what happens is that if you put voltage on this thing, it will deform and it will undergo an in-plane expansion. This expansion is connected to the mechanical properties of the materials, the Young modulus, the dielectric properties, and what I mentioned now is the voltage divided by the thickness squared. So these are our systems that are not new. It was found by Röntgen initially, the X-ray guys, and it came to the forefront about 20 years ago because we found out that with the right polymer, then you could have a deformation that is rapid, versatile, and pretty big actually. And so that was interesting in the context of soft robotics. This is one example of a solid grid burst. So when you apply voltage, it opens, and when you release voltage, it closes. And there are many sort of things, war like robots, robotic arm wrestling, all sorts of things. But what we thought of, we were seeing that was a bit different. We like to think of this area extension as a sort of growth. And this was interesting to us because, well, if you look outside, you will rarely see a leaf or a petal that is flat. And often this non-flatness, this 3D shape, is due to non-homogeneous growth or anisotropic growth. And one nice illustration is this algae. At some point, its growth has this concave shape. But since growth occurs mainly azimuthally rather than along the radii, then this concave shape flattens, as you can see here, and then take on this saddle shape. So we wondered if we could use these dielectric polymers to generate these 3D shapes, and even simpler to start with, if we could generate mechanical instabilities via inhomogeneous growth. So we did something as simple as we could, as mobile as we could. So we have a circular membrane, that's the pink stuff, with a circular electrode, that's the black stuff here. This floats freely on water, so the boundary conditions are free, it's not clamped. Then we contact the black electrode in the active part with a thin metallic wire. You can kind of see it on this picture. And water is connected to the ground. So in the system, water plays the role of the second electrode, the down electrode. So you have this thing that is, all the pink part is passive, all the black part is active. When we apply voltage to this, the black part tries to expand. It's initially flat, obviously. That's what you can see on this picture. The red line here is a laser line with an oblique incidence, and you can see it straight here. If I can find the mouse. And so when you increase voltage, the black part tries to expand, but the pink part doesn't move. So the black part gets more and more constrained, and at some point it bubbles. And this is what you can guess here. You can see that the laser line is deflected. Well, and I forgot to mention that the voltage we're using are pretty high. Here it's about 5 kilovolts, 2 kilovolts, something like that. Okay, so there you see three morphologies that we can get depending on the electrode size. So if the electrode is small, and we'll see what small means, 1 centimeter here, that's the raw picture. You can see here the laser line, so you see that it forms a bump. And this is the extractive profile with the deflection that is a bit amplified, so we see better. If we are a tiny bit bigger, so 2 centimeters in that case, you see that there is this oscillation that is appearing. It's clear on the deflection. And if you go even larger, then most of the deflection most of the deformation is located near the edges of the active part. So these 3 morphologies, we can explain it first qualitatively. We can understand it rather easily, because we are looking at so that's an elastic problem, but an elastic problem on foundation. This introduces a length scale, because when the membrane tries to buckle, there are 2 energies that are competing: the bending energy that tries to have the smallest radius of curvature, and the gravity, because when you buckle, you have to lift water, so you pay a cost if you get out of the plane. And the comparison between these 2 energies gives a length. It's called the elastic gravity length. It compares the bending rigidity to the weight of the water, to the 1/4. And what matters here is that this LEG is a bit more than 1 centimeter. So when the electrode is smaller than that, then the smallest length is the length of the electrode, and so it's favorable for the system to buckle only on the electrode side. When we get bigger, then you can form one oscillation, which wavelength is the LEG. And when you get even bigger because of axis symmetry, then it becomes hard to do these ondulations, and then you'd rather locate the deflection near the edges. Okay, so that's pretty quantitative. Then we can be a bit more quantitative, and to that end, what we did is solving these plate equations, so the Foppel von Karman equations that I did not write, with the boundary conditions are free. There's a central circular part that is growing, that undergoes the stress that depends on the voltage we apply. And I think that's it. And if we solve that here, I plot the amplitude of the deflection normalized by this LEG as a function of E0 is essentially the voltage actuation. So that's for a small electrode. Plane is the numerics, and dots is the experiment. You see that the argument is reasonable. Say there's no fitting parameter here, and the shape, if we compare, it's also pretty good. And if we go to larger electrodes, then the argument is even better, and the shape is also quite good. So we have this numerical tool that we use then to study a bit more systematically the effect of pre-stress on the buckling threshold, the other situation also if we're not on water, obviously the size, the effect of the size of the electrodes, all this sort of stuff. But to finish this part, I'd like to go again to this shape changing that I mentioned in the beginning, because here I talked about this algae that changed shape. That's not really what we are doing. We are really we have one part that buckles. It's just a buckling instability, and we are not able to prescribe the shape of this. And this is because we have this system that in some sense is very discontinuous. One part is growing, one part is not growing. Then if you want to prescribe the shape, as I mentioned, what you have to do is to prescribe a new metric. So prescribe a growth, a gradual growth that would be a way, or an anisotropic growth. And we tried both strategy. And the way we did that is to play with the thickness, the local thickness of the membrane, because you might remember that the actuation depends on the voltage divided by the thickness squared. So playing with the thickness was the easiest way for us at the moment. I won't go into the details of what we did there, but I will simply show what happens for an anisotropic growth. So this is the pink stuff. The pink circles are slightly thicker than the rest of the remaining of the membrane, right? So if you put voltage on this thing, the perimeter will not grow a lot, while the radii will grow normally or a lot compared to the perimeters. And this is the recipe to go from a flat surface, a plane, to a sphere or a cone, something with a positive Gaussian curvature. And it turns out that if you look at this picture, so the experiment there is a the same as before. The membrane is floating on water and a metallic wire here. And you can see that the buckling profile is quite different. We now have this undulating pattern. You can also see that this membrane starts to burn here because this method actually is pretty hard to implement, to put in place. And that's why we did not go very far with that. But I say a word now about this. Because as a conclusion, I told you that I showed you these electroactive polymers and how thinking of this in-plane expansion as an artificial growth allowed us to try to look at other kind of problems. So, for instance, this inhomogeneous actuation. So we have here one spot, but then you could imagine playing with local instabilities everywhere on the polymer. We could do that, and we saw also this strategy to prescribe really the shape of the membrane. And okay, I mentioned that it was a bit hard with this PVS method. Funny enough, a few years later, in Dave Clark's group, they were able to actually use this kind of strategy to get remarkable deformation. Though I must say that the manufacture technique here was completely out of my reach. It was it's pretty subtle. The other way you could do this sort of shape changing is to actually use a system that is simpler to actuate, and that's what Emmanuel did in the group afterwards. He's playing with pressure actuation, so his baromorphs here, he inflate them, but using exactly the same ideas with anisotropic in that case. Expansion, then you can get these quite significant shape changes. You can see this cone or this saddle node shape. All right, so that was it for these polymers. Now we're going to switch gears completely and go in the realm of memory and pathways. This is the work I did in Martin von Hecke team at Amhof in Amsterdam. And what we try to do is use the thing you're seeing here, this shiny thing, to study memory effects in material. And I will start with explaining what I call memory and the link with these pathways. My definition of memory is extremely broad. I will call memory any form of history dependence of history dependency in a material. So that's not very restrictive. And to explain that a bit, we can look at a few examples, two examples that happen in this crumple. The crumple is actually a system I find extremely interesting. That's super mundane. That's nothing. Though it's also extremely complicated. That's a system that has many secrets and many complex behavior. And so as I said, that's why I picked it as an example. It has two forms of memory at least. So the first one is not so complicated. It was found in Chicago in Tom Witten's and Sid Nagel's team. They were measuring the height, so they put their crumple in the tube, and they measured the height of the paper as a function of the weight that sits on the head of the crumple, right? So they start at these blue dots here, use my mouse here, where the dotted line is, so 1.6 kilograms, and then they decrease the weight, and so the height increases. Okay, these are the blue dots. They increase and increase and increase. And then from there, they increase the weight again. So these are the red triangles. And you can see that they match fairly well the blue dots. And what they did then is go slightly larger than this 1.6 kilograms, and they went to 3 or 4 kilograms. And then they did exactly the same thing. So they decrease the weight again. And what happens then is that we are on these green dots. We are following these green dots. So in other words, the behavior, the height behavior of this paper depends on the highest weight it underwent before. So this the form of memory. That's the memory of the highest input Another one, for which I won't go into any details there, that was found a bit later in Schmuel-Rubinstein's team by Joachim Laini, is a memory that is linked to relaxation. The relaxation of a crumple is not monotonic, and what they found is that the relaxation depends. So you take your crumple, your paper, you compress it for a certain time, then you decrease, you relax a bit this compression, and you measure the relaxation force. And what they found is that this relaxation force depends on the time the crumple spends under this high load. And I think it's like spin glasses, but I don't want to say a stupid thing there. But the important point there is that this crumple also can sort of remember the time it spends under a certain compression. So these are only two examples of memory, but really there are many different phenomena that can occur in a wide variety of physical systems. Just to mention a few, granular is a good example. Foams, melts, glass melts, or polymer melts, magnets, mostly disordered or complex material. And most of these time-dependent effects are not new. But what has been more recently found out is that you can find a phenomenon, two similar phenomena in systems with completely different physics. So this is somewhat puzzling, and what some people have tried to do is provide sort of unifying framework for these memories. And what they did is this point of view they developed links the memory to a change in the state of the system. So you have your memory forming system, you apply a field to the case. It puts it in a certain state which has a certain signature over the response of the system. If you do that again, maybe a different kick or higher kick or whatever, you put it in a second state which has another signature over the system's response, and so on and so forth. And so this, if you manage to get this sort of directed graph that we call a transition graph or transition array, then you have a sort of map of the memory regardless of the physics of the system. And so simply looking at this directed graph, the topology of the graph and the properties of the graph can tell you something about the memory phenomenon at stake. So that's very interesting, but well, you simply have to look at this crumple again to guess that accessing these states, this 1, 2, and 3 that I drew in, is super hard experimentally. You following the states this crumple reaches, and even defining the state is experimentally extremely hard. And actually, numerically, it's also for granular, you get maps that are gigantic and horrendous, and it's very complicated. So there, what we wanted to do is really create a sort of model complex system, something that would be complex enough so that we have this sort of pathways, we can navigate through different states, all the while being accessible to us and experimental. And so this shiny thing again is what we've tried to do. So this is a corrugated sheet. This one is made of mylar, so that's why it's shiny. And when I compress it, yes, it works. You can see, so I'm compressing it, and you can see defects that pop up in the group. And these defects are reversible, and more importantly, we can directly see them. So we have a system now that journeys through these different states, and that we can follow live. And so now what I'm going to try to do is to show you how this sort of system helped us to get a better grasp of these networks, these transition networks that I showed you. All right, this is still very complicated. You see there are many grooves, and mylar is not even elastic. There are plasticity everywhere, so it's still too complicated for us. So what we did is we took our favorite material, so it's still VPS, but that's the same thing as before, except that this one is blue and not pink. And we made this small grooves in there, so that's about 1 centimeter high. And we have only 3 grooves, you see, 1, 2, and 3. So that's a half cylinder, I cut it in half. Now I'm compressing it, and you can see that the groove locally and sequentially snap through, right? 1, 2, 3. Oh, oh, oh. Now, if you look at the mechanical response here, so the force as a function of the displacement, in red is compression, you can see 3 force drops that correspond to the snapping events, and in blue, 3 force jumps that correspond to the unsnapping events. Okay, so this is simple. We have 3 states that we visit during compression. Now, let's look at these networks, these transition graphs. And for that, the protocol we're using is a bit more complicated, but not that should be still okay. From 0, we compress up to a value. So here it's 0.5 millimeter and then back. If you look at the movie here, the third groove snaps through, as you can see. And if you look at mechanical response, you see a first hysteresis loop that opens up. So what we are seeing here is that in this system, in these groovy sheets, each groove behaves as a sort of 2-state hysteretic element, a sort of mechanical bit. In the context of memory formation, this is called a histron. So I will call that a histron. But really, that's a bit something that can be 0 or 1. And so based on that, I can label the state reached by the system. So each groove can be snap, I will call that 1, or unsnap, I will call that 0. So in that case, from 0, 0, 0 state, I reach 0, 0, 1 state, where the third groove snaps. And so the first part of the transition network looks something like that. From the ground state, you reach 0, 0, 1, and then back. Now, I compress a bit further to 0.55. So the third groove snaps through, and then the middle groove, the second groove snaps through. You can kind of see there. If you look at the mechanical response now, you have a second hysteresis loop that opens up here, and that connects to the first one during release. So we reach 0, 1, 1 stage, and then back through the same path, right? And then, of course, we go even further, 0.75. The first groove snap through. We played quite fast. Let's try again. Back. And the third hysteresis loop here, reaching state 1 on 1, and the full graph for the system. And you can do that 10 times, you will have 10 times the same sequence. The sequence is not random. All right, so we have our first network for the system. It's not the most exciting one because it goes 3 to 1, 1 to 3, but still that's a first network. And then the second question you may ask is, well, can I get something a bit more exciting than this one? And since we are playing with a macroscopic system, we decided to play with the boundary conditions. Namely, here what we do is we impose a tilt on the bottom plate of the system. So we impose an angle alpha. So I'm playing with the same sample as before. So if there's no tilt, we have the network we know well now. And as I tilt, at some point, I will find out a slightly different pathway. It looks very similar, but for this green state, now there's 0, 1, 0. And if you keep on tilting, I will find a third one, and a fourth one, and 5, and a number of different grounds. Right, so if we play with the boundary condition, we can indeed tune the pathway we get. So now let's try to see what this thing tells us, because there are things to understand there. And for that, we need to again look at the first network, and we need to understand properly what these networks mean and what they imply. With this, what this network is telling us is the first one again is that the third groove has the lowest snapping threshold. It snaps first, then the second groove snaps through, and then the first groove snaps through. I schematize that with this bar diagram. The top part you see, so 1, 2, 3, and you see the line here is the smallest, so 3, 2, 1. This shows how the snapping threshold are ordered. Then during unsnapping, it goes the other way around, right? The first groove, then the second groove, then the third groove. So it's 1, 2, 3. Okay. This bar diagram it's simply a way of showing how the thresholds are ordered. And what is interesting there is that if I give you the bar diagram, you can draw this network. And if I give you the network, you can control the bar diagram. So the two information are equivalent. You can go from one to the other. And it turns out that you can play this game with all of these networks. If I give you one, you can draw the other, and vice versa. And this actually is pretty interesting, and it's more significant than it might look. That means that if you want to model this sort of pathways, the only thing you need to have is 3 histrons, so 3 bits, that are uncoupled. So you decide what the thresholds are, and then you get this pathway. This is a very classical model in this realm, in the realm of memory and hysteresis. It's called the Presac model. So we call this network Presac networks. And incidentally, it means that this sort of network are reminiscent of a classical form of memory that is called return point memory. Initially found in magnets, and essentially that's the memory of the highest input, the extremal input, and that implies a certain hierarchy in the loops of the networks, but won't go into any details there. But so we can model this Groovy sheet with an assembly of uncoupled bits, and somehow we found that fairly surprising, right? Because a histron in that case is actually a groove. So if your groove sheet and your 2 neighbors are snapped, it's hard to imagine that somehow it won't influence your own thresholds, and that the grooves are not in a way or in another way coupled. And it turns out that we found evidence for this coupling, the different pieces of evidence, and the most striking one, I think, is this graph. Because I showed you 6 networks, but actually there were 7, and this 7th is a bit special, which is probably not obvious there at this point. So if we look at the snapping of this guy, there's nothing special there. It's you see a gray to green, green to red, red to black. It's 2, 1, 3. It's regular, no joke. The unsnapping is a bit more sketchy. If you look, if you look at the left part, yes, from red to green and green to gray, you see that the first groove unsnaps before the second. So if I look at the bar diagram, should look something like that. So 1, 2. I know nothing about 3 yet, but okay, fair enough. Now I look at the other part, right part or left part, this part, and I go from black to orange and orange to yellow, and I decompress. So this is telling me that the second groove unsnaps before the first one. So this tells me that the bar diagram should look like this. So 2, 1, and then 3. And now you see that these 2 representations that do not agree with each other. This one is 1, 2, and this one is 2, 1. And so that means that you simply cannot use this. You cannot represent your network with this sort of bar diagram. Another way of saying that is that the information of the thresholds is not enough to get this network. And the thresholds are influenced by how the state of your neighbors. We call this network a scramble network. It still obeys the topological rule of the memory I mentioned before, the RPM, but still it's a clear evidence of interactions in the system. And why that was interesting for us is that that shows that you can have coupling in the system. And as you might imagine, if you add a coupling into a model of histron of bits, then the number of pathways you can get explodes. There are many different pathways you can get. And so we decided to look a bit more in detail into these pathways of coupled histrons. And to that end, we manufactured another sample with increased coupling, and we played exactly the same game. So we compress it, we look at the pathway, we tilt the plate, and we do that again. We found 9 different networks. Okay, cool. Out of these 9, 5 were scrambled. So already that tells us that indeed, when you crank up coupling, then you find more real graphs. But out of these 5, there is one, this C8, that is special to us, was particularly interesting. And to finish this part, we will look at these 2. So here you have the C7. So this one is scrambled, but it has the right topology, the return point memory that I've mentioned before. This is a C8. This is a wheel one. It looks extremely similar to the other one, but for this red arrow that comes out of the green state. Okay. Actually, this simple arrow that ruins the hierarchy of groups, the topology rules of this return point memory, and that creates, or that's the sign of a new form of memory, say a new behavior, at least a different behavior than we had before. And this behavior we can illustrate it by submitting these 2 samples to the same sort of protocol in which we compress enough to reach this orange state, 011. Then we release a bit, so we reach the green state, 010. And then we compress again to the exact same value. So we apply 2 times the same compression. So in the return point memory case, well, that's memory of the last extreme of inputs. We go back to the orange state. In the other case, however, you can see that applying the same compression puts us in this 110, this red state, and from there we are trapped in this blue to red loop. But what is important there is that the response to the first and second driving cycles, even though these cycles are exactly the same, is different. And this, you could think of it as sort of very basic computing feature. This actually counts to 2. That's very modest, but that's still the first step in this realm. So what we saw here is that these corrugated sheets allowed us to evidence this sort of elastic memory, where the only ingredient we have is this snap-through instability. And that since the system is macroscopic, we can sort of tune the pathway we get. And the system is very empirical, right? We do not have a great deal of control over the pathway, yet it was interesting because it still has this coupling thing, which allowed us to put the first step in this realm of coupled histones and finding out that that's a way to get these more complex pathways that might be a kind to basic information processing and stuff like that. From there are many routes you can take. You could, for instance, wonder if you could say something sensible about the space of these G graphs. Can you classify them according to certain properties? So that's a very theoretical question. One thing I'm particularly interested in is could you get more complex T graphs that look like other forms of behavior found in other complex material. And the last part, which will be the topic of the last part of this talk, you would need to wonder if you could design this pathway. Can you create a system where you know which pathway you would have? And what would be interesting is, can you design a complex pathway, since there is not trivial, like more complex information processing or multi-periodic things and stuff like this. So the question in essence here is can we design a histone that we control? Yes, we control the threshold and we control the coupling. So that's something again with Martin and with Mathis, Martin, and Colin, that were 3 interns that succeeded into each other. So we like mechanical systems, and a histone, if you remember, it's just something that has 2 states and that goes historically from one to the other. And so one simple idea was to try to do that with a beam. The beam, a vocal beam, can be vocal to the left or to the right, so that's two states. And I can play this movie. This is a mylar beam. I push it laterally, you see it deformed, and poke, then it's not free. So the way it goes from one state to the other when you push it laterally is this fairly brutal transition, this snap through transition, which doesn't work, but it's not very bad. Okay. So then the question, the previous part was fairly abstract. This part will be way more down to earth. The question I'm asking is, can I design a system? Can I design a throbbing beam, a beam that goes from left to right? And I have one important spec here, is that what I want to do is I push on one button, the beam goes to the left. I push on the same button, the beam goes to the right. The excitation should not depend on the state the beam is in. That's important. So we first thought it would be fairly easy. We thought that's okay. We put two pushers on each side of the beam. We find a smart mechanism so that when we push on something, the pushers get close to the beam, deform it, and poof, that toggles. And so we had Matisse for a few months, and we put him in the lab, and we said, okay, easy, do that. And he tried many things, and it never worked. And he tried really many things. And it turns out it could not work. If you look a bit at what happens when you push the beam laterally. So these schematics are actual beam shapes. They are calculated in that case. The deflection is a bit magnified again, so it's better, but these are actual shapes. So when you push your beam, it deforms, and it will snap when it reaches this pure Segel mode, this S or anti-S in that case mode. That tells you that well, if you want to push it with your tip there, you have to reach at least this dotted line. And so when you have two tips in front of each other, they will bump into each other, and if you can do whatever you want, they will always prevent the beam to snap. There's no way around. That doesn't work. At least we haven't been able to do, and I think we've tried a fair amount of configurations. And so in some sense, what we need to do there is to have earlier snap, something, a beam that would snap earlier than that. So I was a bit pessimistic when we found that. And Matisse luckily was not. And so on his last day, we were working in the lab, and we figured out that if you your beam, you push it, and then you push a second place. So you have two-fold pushing. Then you could have earlier snap through, and that gave us the beams, which was using this sort of two tips pusher, and this is what Martin worked on. So you can see here what happens when you push your beam with this sort of two tips pusher. It deforms the same way, but what is interesting to us is that it snaps before the pusher reaches the middle path. So okay, now we have something to study. So we decided to study this instability. And well, that's when oh, maybe I should mention that yes, that's one thing interesting to notice also is that even though the problem seems actually it's not a super complicated problem, but the phenomenology is actually fairly richer than we expected. It turns out that you can snap through as is represented here. We're following this scheme. That's a one-step snap through. But you can have something a bit more complicated, and I will try to stop the movie at the right moment. So I'm pushing the beam with the pusher here, and I have to stop it now. Yes. And you see that the beam touches the pusher now only at one spot, not at the two spots. Now, obviously, here I stopped the movie, but you could also stop the experiment that does the same. This position is stable. And so we have this second way of snapping through, which is what we call a two-step snap. If you keep on pushing, then the beam eventually goes the other. So we have one-step snap through, a two-step snap through, and since we have a top-down symmetry, you can do that forming an S or an anti-S. So the bulge can be in the top part of the beam or on the bottom part of the beam, right? So, well, we decided to study this and try to understand that, and that's when the first COVID wave hit, I think. So it was a good incentive to do that theoretically and numerically, and that's what Martin did. Essentially, what we do is that we minimize the energy of the beam, the bending energy. We neglect the stretching in that case, and we impose so clamp boundary conditions, and we impose three constraints. So length constraint, the length of the beam is preserved in extensibility, and inequality constraints, so where the beam contacts the pusher, it cannot go through. And the other thing we do, and which is suggested actually by these pictures, is that we perform a beam expansion. So we write the shape of the beam as a function of the buckling modes of this clamp beam. So I represent here the first three modes. So this is the first buckling mode, the S mode, and the W M mode. And this simplifies greatly the expression, and in particular the length constraint, the extensibility, becomes rather simple. So here for three terms, the sum of the mode amplitudes, the squared mode amplitudes, is equal to 1. So they lie on the sphere. And why is that interesting for us? At least to represent that is that even though we have three parameters, they are dependent. They are not independent. So two parameters are needed to model the shape of the beam. So I would call these theta and phi. So these are just spherical coordinates. It's not really important. What matters is that now we can plot the energy landscape of this beam in a plane as a function of these two parameters, phi and theta. And so any point in this landscape corresponds to a certain shape. Yellow means that's high energy, and purple low energy. So, for instance, these blue dots here at the middle of the landscape correspond to this left or right bubble shape. I don't know, the minimum of the global minimum of the energy, and these other points are phi equals 0 and pi. Theta is equal to pi to the other side. And so now the question is, well, how can I go from one value to the other? And this is obviously where the pushers come into play, because as you saw in the movies, what they do essentially is that they constrain the beam. And in terms of energy landscape, what they do is that they create forbidden regions. They are part of this landscape where you cannot go because the pusher is here. And this we can calculate, and we can visualize what happens in this landscape. So this is what happens at the beginning. So we have these two white circles that correspond to the two tips. Each tip brings its own constraint. And what these two constraints do is that they pull the beam out of its value of energy. So the way you can think of it is you have a marble at the end of a slope, and you have these two walls that trap the beam or the marble and pushes it out of the hole. So you push it, they create a new local minimum where the beam is trapped. You see that as you push it further, the forbidden regions they increase, as does the deformation, to the point where you push your beam far enough, and now there is a negative slope in the energy landscape, and so your beam or your marble or whatever will go down this slope. So in that case, this slope brings you directly to the new global minimum, so the other side of the bubble. And so one thing I should mention is that while I can calculate the positive shape at any moment, what happens between these states, so the last stable state and the new global stable state, I cannot say. I don't know how you go dynamically from one state to the other. I just know when I snap. So that's the one-step snap through. If you're looking at the two-step snap through, so the position of the pushers is slightly different. Essentially the same thing happens. You push your beam out of its nest up to the point where you have still a negative slope that you will follow. But as you can see, is that this happens slightly earlier. And so there is actually still a local minima that exists and that you can reach when you're being pushed by the pusher. And this is the local minima, and that corresponds to the beam contacting the pusher on only one spot. And then from there, if you push further, then obviously you get to the other side. So that gives us the tool to study this instability and understand it is one step, two step. And then we use it essentially to map out the problem. So we have these four scenarios. Blue corresponds to the anti-S shape, red to the S shape, and light color to the two-step, dark colors to the one-step. And I represent here the state diagram. So here are the position of the top pusher, bottom pusher, and ZB is negative because I forgot to mention that the bottom pusher is always on the down part of the bottom part of the beam, while the top pusher is on the top part of the beam. And you see that there is this symmetry line along ZT equals abs ZB, because the problem is symmetric. And there is these two small pockets of two-step events. And we can, of course, also look at when those snapping happen. Red here means that you have an early snap through, so you snap before reaching this middle line, and you see that there is these quite large regions where you can indeed have an early snap. So that's great. There are still things we do not completely understand about these, but we have reasonably well understood these. However, I told you at the beginning of this about toggling beams, or something that would go from one side to the other, and I still haven't shown you anything like that. I'm just showing you this simple snap through when I push laterally, and so that's the last thing I will show you. How can we do a toggling beam? So there are different strategies we could employ, but the one that Colin counts, I think I like it a lot. So when he came, he said that we were pushing the beam, so the beam is static and the pusher is going towards the beam. And we said we don't need that. What we need is that in some way or another, the beam and the pusher contacts each other. And so what he said is that I can have a static pusher close enough to the beam. I compress the beam, it deforms, and at some point it will touch the pusher, deform, and maybe snap. And so that's what it did. It turns out that there is exactly the same phenomenology. So one step, two step, S, anti-S modes. But this is a state diagram, an example for a certain position of the pusher. You can see that there are many gray squares. The gray squares correspond to configuration where snap through doesn't happen. And also now the state diagram is skewed. There is no more top-down symmetry. But still we have this S, anti-S, one step, two step. And to finish this, I will show you an experimental result of this. So we picked these two positions where the stars are. So the two step here, one step here, and we built the corresponding system. I should mention that even though this looks easy, you have to have something that is very well aligned, otherwise it won't behave as you expect it to behave. And so there was quite some work in, we built actually our own testing machine very well aligned with a protocol to align very carefully everything. So mounting this is actually quite some time, more time than you would expect, which is than I expect. So the movie is a bit complicated. You have here the beam. It's about 10 centimeter long, and I think 1 millimeter, I think, if I remember correctly. We will compress it, it will buckle. It will first touches these two pushers that are now static. It will deform, and you will have first a two-step snap through, and then we will go the other way. We will release the pressure and do that again, and we'll have the one-step snap. So let's go. It snaps, one step, move, second step, release, and then the two-step. And now we have this beam that indeed can toggle from left to right under this single input, which is compressing it. That's quite, I find it quite mesmerizing to see this beam. So now what Colin is doing is now we have this system. Again, there are a few questions we need to answer about really the instability. But now what he's trying to play with is so that's not really an issue. We could discuss that if you want. But still, you can wonder what sort of sequences you can have with this system if you put several of these beams. And even more interesting question I find is we found ways to couple these beams. So you take several of them and you couple them, and then you can start wondering for a given sort of coupling, is it ferro or anti-ferro, and what sort of sequence will you get if you do that. So that concludes my talk. I hope I showed you a few examples of instabilities and how they allowed us to study these two different forms of complexity. So this shape forming, patterning, and these memory effects. One thing I find interesting is to couple the instabilities, because that's a cheap way to increase greatly the complexity of your system. So, for instance, I mentioned the coupled beam before. This is something completely different. These are bumps in the sheet that I compress. When you have a bump in the sheet that you compress, you have a wrinkling pattern that appears. But now here there are three bumps. These are three dots that you can see here, and you can start wondering how does the wrinkling pattern, how do they interact with each other, so increasing the complexity that way. One thing that I'm starting, I will start soon, is also playing with the material. So because so far we play with elastic things, so there's no time, everything is quite static. But then you could start wondering, what if I was playing with viscoelastic things? So this is a viscoelastic beam. I push super quickly and then I wait. And if you wait long enough, then viscoelasticity both makes the thing go to the other in the other direction. And so this, I think, there are many questions, because even the simple description of this beam, I think, is hard. I don't know how to do it yet, and that also induces a time dependency in the problem that might, I hope, help go towards this time-dependent memory that I mentioned earlier. And finally, one last aspect, this is what I'm doing at the moment in Brussels, is to couple these elastic structures, these slender structures, with another ingredient, in that case, a liquid. So this is something I do in Fabian Université in Brussels. So we have two glass fibers that are in a liquid, so that's oil, and we pull them. And if you don't pull them fast enough, they will just get out of the liquid. And if you pull fast enough, they will touch each other and they will stick to each other. This happens, actually, we're not really sure why this happens. The deformation of the interface is important, but it might not be the only thing that matters. But anyway, the important point here is that this coupling is also a nice way to try to understand something about create model systems of very complex situations. So for instance, these fibers are a very model way of understanding what happens in a bead tongue, because the bead tongue is this, you have all these hairy things that stick to each other and help capturing the nectar and stuff like that. And so I think with that I'm done, and I thank you for attention. If you have any questions, I'm happy to.